about this is how is the mean stress the matters. So we talk about several. This is a criteria, and one is the Gerber line criteria, one is Goodman line, and one is Soderberger line. So Gerber line is a very good one, and however, so it contains the power 2. So this is the quadratic. This equation is a quadratic equation. So this is more complicated. On the contrary, the Goodman line, and it contains only the linear the terms. So we are going to focus on the Goodman line. So this is so this is the material. This is for the ductile material. For brittle material, and we use the Kc. Kc is a static stress concentration factor, instead of Kf. And the Kf here is a fatigue stress the concentration factor. Can you guys write down? And because we are going to use this is the concept very often. Fatigue stress concentration factor and Kf. F means fatigue. Apply Kc on the alternating component also. This is for the brittle material. We only focus on the ductile material. Questions regarding this slide? By the way, where are the other guys? Huh? You can go outside. Okay. So failure line, the Gerber line is the best predictor of failure, difficulty in calculations. And as I told you guys, it contains the power 2 for the second term. And conservative, Goodman line is a conservative and simple to use. And Soderberger line is very conservative. It's too conservative, and we will waste a lot of the material, a lot of energy, a lot of money. Okay. So we should be conservative, but not too conservative. You understand? Okay. So this modified Goodman line. Modified Goodman line is very complicated. You can see this is the blue, the bold lines. And so what does it say? It says that if your stress level is located within this is the shape, that means your specimen is safe. If the stress level is located on either on any of these lines, that means that the critical state, okay? And outside this is the shape, that means it's very dangerous for your specimen. And the specimen might fail at any time. You understand, guys? So within this line, it is safe. On the boundary of this shape is critical. Outside this boundary, it's dangerous. Okay, guys? You want to have a MATLAB program project to finish this one? No, right? Okay, everyone. Okay, everyone. Just ask me. Then I give you another assignment. So this modified Goodman criteria. So this is a graphical representation. So here is the equations. So each of these lines, and they are described by using these equations. Now, questions so far regarding the Gerber line, Goodman line, Soderberger line. No question? So, no questions. Then I'm going to talk about the next slide. This is the Paris law. And then I'm going to give you an example. So we want to learn the fractal mechanics approach to fatigue failure. A fractal mechanics approach means that we are going to use the stress intensity factor. And so understand the different fatigue crack propagation regimes So we have three stages: stage 1 and stage 2, which is described by using the Paris law, and stage 3. And then we talk about the Paris law. What is the fracture mechanics approach? As I said, when we use the concept of stress intensity factor, and for two case scenarios, for static and cyclic. And for static, and I told you guys, I told you on how to, for the static problem, on how to predict the failure of the cracked body. So step for static, and we apply the stress, and then based on geometry, material property, and apply load, and we can get a K, right? We can get a stress intensity factor K, and then we compare this is the actual stress intensity factor K, and with the KC, and KC is a critical stress intensity factor, which is a mechanical property of your material. And we compare this K and this KC. If this K, definitely sometimes we use the bigger number as a safety factor. Okay, so K and KC. If the N multiplied by K and equals KC, and we say so this is critical state. And so usually we have this is the stress intensity factor, and let the product of these two guys equals KC. So this is the material parameter. And it means that, and if you want to select a new KC, you need to select another material. So this is actual K. This is a stress intensity factor. The stress intensity factor. Stress intensity factors. So N is a safety factor or design factor. The usually is greater than 1.0. So we use this equation to check on whether we reach the critical state or not. So this is for the static loading. However, for cyclic loading, it is another story. Okay, you can see the K. So this actual K can be very, very low than KC. However, the time, the number of cycles, is involved. So this is very, very dangerous. Even though this K is very, very low, but if we have the cyclic loading, the number of cycles is involved. So as the time goes, even we have very, very low stress level, and still we have the safety issue. Understand, guys? Cyclic loading because the number of cycles is involved, the time is involved. So the design may be safe considering static loads, but any cyclic loads must also be considered. So this design course actually is preparing you for the senior design, right? For senior design, you will design your own system, right? So when you design your own system, you need to consider, so this system, this mechanical component or mechanical system, and what kind of loading conditions that this guy usually experiences. Whether this is a static loading only, or under some conditions, and this component or system will experience this is cyclic loading. If cyclic loading, you must consider this is a fatigue. This is a fatigue, cyclic loading, fatigue strength. You are very careful. Otherwise, it will be very, very dangerous. Also, because the cyclic loading always happens at a very, very low stress level, it is more dangerous than the static loading. Static failure. And so last time we talked about this is the fundamentals of fracture mechanics, and LEFM stands for linear elastic fracture mechanics. So in 1963, The ideas of LEFM were applied to fatigue crack growth by these three these talented professors, Paris, Cummins, and Anderson. So Anderson now is Professor Anderson is still alive. He wrote a textbook, which is commonly used one. And Dr. Paris is my faculty mentor, and he passed away 2 years ago. So Cummins, I have never seen this talented professor. These three guys are called the fathers of the fundamental fathers of reaction mechanics. Okay. So for given cyclic loading, we define delta K. Delta K. What is delta K? Delta K is the range of the stress intensity factor. So because your stress level is alternating, right? As a result, the K is alternating also because the K is dependent upon the stress level sigma. If the sigma has a range, and the K will have another range. You understand that? Because the K is determined by the stress, which can be found from the delta sigma. Delta sigma is the stress range and the geometry of the cracked body. So we can find this delta K is playing a very, very important role. And then Paris law, Dr. Paris, the rate of crack growth depends on delta K in the following manner. So this A is the crack length, and delta A is the crack length, the increment of the crack length, and delta N is the number of cycles. This is delta N. So this one can be written as the derivative of crack length with respect to number of cycles. So this equals C multiplied by delta K M, and C and M, and they are material parameters. Can you write down? And what is the C's value and M's value? And you need to do the experiments for this material and to obtain experimental data. Write down guys. And C and M, and they are material parameters. Questions regarding this slide? So Paris law, this is the Paris law. Dr. Paris found this law in his early 20s. Right? So this is very, very impressive achievement. Dr. Paris had been working at WashU for many, many years. And after he retired, he moved to SLU. Right? And moved to our department. That is the reason. And Dr. Paris and we interacted to do something together. So here is the delta K. You can see delta K equals lambda delta sigma pi A. So delta sigma is the range of your stress level, and then based on this equation, we can have the range of the stress intensity factor. So you can see constant C and M are material parameters that must be determined experimentally. And typically, M is in the range of 2 to 4 for metals and 4 to 100 for ceramics and polymers. And fatigue crack growth. So this is I talked about this stage last time. So we have the 3 stages. So first stage and second stage and third stage. The second stage is for this common log, this is delta K. So this is the DADN. So this one is almost a straight line. Okay, so you can see this one can be described by using this equation, which is named after Dr. Paris. So here is a very, it goes very, very slowly. Here is very, very steady. And this is the third stage. So this crack grows very, very fast until the component fails, just like the cleavage crack probably. Questions regarding this slide? Also, last time I also told you guys. So this is the 3 stages. They are very, very similar and to the phenomenon. Can somebody remind me what that phenomenon is? Dylan?
No idea.
Creep. What? Yeah, creep. Write down creep. CREEP. The creep For the crepe and the component behaves is very similar. Crepe, yes. So the three stages, regime one called stage two, stage A, stage B, or stage C, or you call it regime. This is the same thing. Regime A, fatigue crack growth. This is one delta K. The range of the stress intensity factor is lower than its delta KH. H is the TH is the threshold. Write down as TH is the threshold level or the critical. And where delta TH is the threshold stress intensity factor, and the rate of crack growth is so slow that the crack is often assumed to be dominant or growing at an undetectable rate. It's very slow. So delta KH, TH can be defined as the value of delta K for which the rate of crack growth is 10⁻⁸ millimeter per cycle or less. So this is the delta KH. So crack growth is extremely slow and represents average crack advance of less than 1 atomic spacing per cycle. If you have taken the material science, you know atomic spacing, right? Atomic, and the spacing. So how is this possible? The crack advances by 1 atomic space, and then you can just back and forth. So by atomic spacing in a single cycle, which is followed again by many cycles with no crack advance. So this is for regime A. For regime B, also called the Paris regime, the rate of crack growth is weakly sensitive and to the loaded ratio because it is equal C delta Kn. So the key parameter governing the crack growth is delta K. So R is not important. So this is delta K, the stress intensity factor range. So how to determine now? If we want to do something calculations, we need to know the initial crack length, right? How to define the initial crack length is 0. So cracks can be detected using a variety of techniques, ranging from simple visual inspection using our eyes to more sophisticated techniques based ultrasonics or X-rays. X-rays is a highly sophisticated one. You can just use that X-ray to detect initial crack length. So if no cracks are detectable by inspection, then assume that the crack is just as the resolution of the detection system exists. So we just make some assumptions. So how to determine the final crack length? The initial crack length, final crack length, and then we calculate the number of cycles. And so this is a specimen can experience before it fails. So how can we calculate the final crack length AF? Eventually the crack can grow to a length at which the material fills immediately. Okay, so we want this this equation to hold. Lambda sigma maximum delta pi AF as let this guy equals Kc, and Kc is the critical stress intensity factor. You understand, guys? And we use this equation, and because Kc is a material parameter, after you select material, Kc is determined. And then the sigma, you know sigma. And lambda, what is lambda guys? I forget. Can somebody remind me? Aiden?
Eigenvalue? Is it the eigenvalue?
Huh?
Is it the eigenvalue?
No.
Okay.
Let's go. Lambda or beta. Sometimes we use beta. Make a guess. You forget everything?
Beta?
Yeah, lambda and beta. Some people use lambda, some people use beta. Lambda is a dimensionless geometry correction factor. Right? Dimensionless, that means it does not have any limit. Geometry means it is associated with the geometry of the problem domain. And correction, we want to use for the correction factor. Right, one more time, guys. Lambda or beta, and we use this one, we call this one as dimensionless geometry correction factor. So this guy's value is dependent upon the geometry of the corrected body and the loading conditions. Right now. Okay, so and we know how to calculate the initial crack length A0, and then we know how to calculate the final length of the crack. And I'm going to give you an example, no worries guys, okay? So crack tolerant, damage tolerant design approach. I'm sorry, here is a so even if a component has a detectable crack, it need not be removed from service. And using this framework, the remaining life can be assessed. The component can remain in service provided that it is inspected periodically. So this is called crack tolerant or damage tolerant design approach. Right? So even though this we know this is a component or system, we have some cracks, but to save money, and we still use it. But you need to be very careful, okay? Just like I'm driving a almost 20-year-old car. It's still drivable, right? But I need to do the check very periodically. 3 months I check one. 3 months. If I have a long trip to drive, I need to have a thorough assessment from these experts. But it's still drivable, right? So if something happens, you can just park near the curbside, just call the AAA and to get it towed. It's okay. So this is a crack tolerant, damage tolerant, the design approach. But for this one, don't use this design approach for any NASA-related missions. Otherwise, you will be very angry with it. Yeah, you are going to the space, right? Any problem can have very catastrophic results. You understand, right? So we need to make sure everything is every component is perfect as far as we know. Questions, guys? It's only for our daily life, okay? For our daily life. That means if something happens, we just park our car near the curbside and call the police or call the AAA. Everything is okay. We will not damage ourselves. But for some case scenarios, we need to be very careful. So fatigue striation. So you can see we can show you this is the breaking in the surface. What the breaking surface looks like. Advancing fatigue crack leaves characteristic marks called striations in its wake. It's very beautiful. I'm going to show you a picture. Striations can provide evidence that a given failure was caused by fatigue. Whenever you see this kind of characteristic, you know that so it breaks because of fatigue. And the last one, the striations on the crack fracture surface are produced as the crack advances over one cycle. That means each striation corresponds to a DH. One cycle, how far it goes for one cycle. I'm going to show you here. It's very beautiful, right? Is that very beautiful, guys? What does it look like? It looks like the lunar surface. Do you guys agree? Some irregular, the rocks, some area they're kind of flat. There's some weak, maybe it's another rover have just a pass here, right? You know what I'm saying? Mm-hmm. So this one you can see, and this line and this line. So this is the crack advancement for one cycle. You understand that? Whenever you see this kind of the striations, that means this is the surface breaks because of the fatigue. So as I said, so here and each of these space is the crack advancement for 1 second. Questions so far? No question. So what I want to tell you is that if given this one, and you can just get, if you are asked, for 1 cycle, how far this crack advances, and you can just measure it, okay? This is, and whenever you see this kind of characteristic, you know, so this is because of the fatigue. So then we talk about residual stress. How can we enhance the fatigue life? The residual stress plays a very, very important role. And then how can we induce this beneficial residual stress? Residual stress, we can do the thermal treatment. And thermal treatment, we can use a through harness, okay, through for the whole the component, or the case hardening. And case hardening, you know case hardening, right? Case hardening, I told you guys, case hardening, we have a sealed chamber, and we put some solutions, liquid or gases, or this is solid materials, and that have small atoms, smaller atoms in the chamber, and then we put our product that we want to heat treat in the chamber also, and then we seal the chamber. Then we elevate the temperature and hold the whole chamber for a long time, and then the smaller items from around in the chamber will diffuse into the surface of the workpiece, and we are heat treating. Okay, so usually after we finish heat treatment and we pull out this workpiece out, and it looks darker. But you can see some looks darker. Also looks I'll say some items. That's a kind of exaggeration. You cannot see atoms, but you can see just like we put some small sands, with some grains, some sand grains on the surface. And so as a result, the case hardening can provide the following benefits. I want you guys to write down. So first, improve the hardness of the surface. Hardness. Second, induce. This is a beneficial compressive residual stress, and to enhance the fatigue life of the component. Two things. Hardness itself. Second, we induce the beneficial compressive residual stress. This is the first category. And second category is the surface treatment. And we do the surface treatment short pinion. And short pinion we use, and this is a bunch of small metallic particles, and to heat the surface we are interested in. Right? So as a result, after the short pinion, you can see a lot of tiny craters on the surface. So these tiny craters induce. This is a beneficial compressive residual. Second one is cold forming. On cold forming, we use rolls. We put this workpiece inside of the rolls. Right in manufacturing, I told you already here. We just compress it and to induce the compressive residual stress. So for the research, for the advanced research, we use the laser pinion. Okay, guys, if you are interested in laser pinion research, call me out of the class. Laser pinion is also, the purpose is also use the laser